So, in classic trust analysis, we go through and use the method of joints, in which we literally work joint by joint and we solve for all the forces and all the members. There are times, however, in which we want only a few forces in a truss. If that is the scenario, we want to use the method of sections. So in this example, I've got a truss. You can see it's got a 400 Newton horizontal force. I've got a 1200 Newton vertical force at point C. The overall height of the truss is 3 meters, and then each one of these sections is 4 meters long. At point A, I've got a pin, which would obviously have an X and Y reaction. At point D, I've got a roller. And so in this video, I'll show you the method of sections in which we're going to solve for 3 forces. We're going to solve for the forces in member EF, in member EC, and member BC. So just those 3. With all truss problems, the first thing you have to do is you have to start by solving for the reactions. So I'm going to draw a free body diagram, and I'm going to just draw it for the entire structure. Okay, so I'm not going to necessarily draw all these individual members. I'm just going to look at the structure as a whole. Okay, and so I know I put some dimensions down, of course. Here I've got 3 meters. Okay. At point A, I'm going to call my vertical reaction AY, my horizontal reaction AX. Okay, I'll go ahead and draw my 400 Newton force here. And then at point C here, I've got this force coming down. That's a 1200 Newton load. Okay, and I'm going to go ahead and show this dimension here. This would be 8 meters. Which makes this dimension here 4 meters. Okay, and last but not least, I'm going to go ahead and show my reference axes, right? So X going to the right is positive, Y going up is positive, counterclockwise moment is positive, and that's what I'm referring to as positive notation. Okay, so the first step, of course, is to go through, now that I've got a free body diagram, okay, showing my forces, showing my reactions, my known forces and reference axes, I'm going to go ahead and solve for these reactions. Okay, I'm going to start by taking a moment at point A, which we know has to balance to 0 if this stress is in equilibrium. Okay, so I have a force of 1200 newtons. Okay, and relative to point A, this would be a clockwise moment, which is negative. So I've got 1200 newtons. Okay, at a moment arm of 8 meters. Okay, I also have this 400 Newton force, and its moment arm is 3 meters. Okay, from A, again, using the principle of transmissibility, right, we can consider the line of action right here along this horizontal line. So I've got 400 newtons at a distance of 3. That's going to be a clockwise moment as well. So I have 2 negative moments, one from the 1200 Newton force, one from the 400. Okay, and of course I forgot a reaction right here, which is what I'll be solving for. At point D, I've got a roller, which will have a vertical reaction. Okay, and so here I'm going to have, based on my notation, this would be a counterclockwise moment, which is positive, at a distance of 12 meters. Okay. When I solve for this, what I get the dy is equal to 900 pounds. Okay, and I'm going to go ahead and box that in, even though that's not the initial objective of this problem. We're going to solve for those forces. I'm going to go ahead and box that in anyway. So now that I know one of these reactions, I'm going to go ahead and solve for the others. Okay. We'll go ahead and use, say, summation of forces in the x direction equals 0. Okay. For this free body diagram, I see I've got AX, and based on my notation, I have AX going to the right, which is positive, plus 400, which is also going to the right, has to equal to 0. Okay, when I solve this, it gives me AX equals minus 400, or we can say that AX is equal to 400, and the pound, that would be newtons, but it's going to the left. Okay, not to the right as I originally had drawn. Okay. And the last thing I have, of course, is going to be a y. There I'm going to just sum up forces in the y direction. Okay. So AY is going up, positive. I've got 1200 going down. Okay, I've got dy going up of 900. All that has to be in equilibrium. That gives me an AY equal to 300 newtons. And it's going up as I originally had guessed. Okay. So now that I've got my reactions, I can actually get to the method of sections now. With the method of sections, what we're going to do is we're going to cut the truss into two pieces. Okay. As I mentioned earlier, I went ahead and identified that we're going to find forces in EF, EC, and BC. So literally what I'm going to do is I'm going to cut through those members. Okay. With the method of sections, you can only cut through 3 members. Okay. When you make this cut, imagine having a chainsaw, and you're literally just cutting through these 3 members, and you're making 2 separate pieces. Each piece of that truss is now in equilibrium. I'm going to solve with the left-hand side. You could also work on the right-hand side. I'm going to do the left-hand side just as convenient, because it's convenience, and I usually just work on the left. But you could solve either the left or the right-hand side. So when I do I'm going to do a free body diagram of just the left-hand side. Okay. And so I'm going to just draw that out real fast so I don't mess up with equations. And when I draw that in, I'm also going to draw in my forces that I know. So for example, AX is 400 newtons going to the left. I had AY of 300 newtons going up. And then I've got a member like this. Okay. I'm going to label this right here as the force in member EF. Notice I showed in tension. That's pretty much the standard. Whenever you cut these members, we don't know if it's going to be in tension or compression. We assume they're in tension, and then we let the equations tell us if we were right or not. So this one was also a member that we cut. I'm going to call that force in EC. And then the last one we cut, of course, was this right here, which is force in BC. Okay, and for convenience, I'm also going to go ahead and extend these and show that they're concurrent forces, right? Meaning that they would intersect each other at this point C. Okay. Making sure a couple things. Let's go ahead and put some dimensions in here. This is 4 meters here. This is 4 meters here. This height here was 3 meters, right? The overall height of the truss. I know I'm going to need this, so I'm going to go ahead and take care of it now. When I look at the slope of member EC, right, it's got a run of 4 and a drop of 3. Okay, so this is a 4 and a 3. Using Pythagorean theorem, we see that this is a 4, 3, or 3, 4, 5 triangle. Okay. And I think everything else is good. Again, I'll include my reference axes here just for consistency. Okay. Now, what we're going to do is going to be very similar to what we did to the reactions, but now we're going to apply it to just this one portion of the truss, the left-hand side. And again, I have all these. Let me draw this a little better here. All these I'm showing in tension. I'm going to go and do, again, I'm going to go after the low-hanging fruit first. So the first thing I'm going to go with is the summation of the forces in the y direction. Okay. So in the y direction, I've got 300 newtons going up. Okay. Coming down, I'm going to have the vertical component of FEC. Okay. And that's a negative, and its vertical component is going to be 3/5. Okay. So I have 3/5 of FEC going down, negative. I've got 300 newtons going up. On the left-hand side here, I have no other vertical reactions or vertical components. Okay. So when I solve for this, I'm going to have 300 divided by 0.6. FEC will come out to be 500 newtons, okay? And since it came out positive, meaning if I take this term and I move it over when I solve, everything's positive, that means I was correct. So it is in tension. Okay, for my notation, I'm just going to write it like this. So I have a force of 500 newtons in tension. Okay. So that took care of this one right here. Now let's go ahead and look at these other ones. Okay. Now, as I mentioned earlier, I noticed that at point C, I've got two forces that are concurrent, meaning that these two forces intersect at this point. So I'm going to go ahead and take a moment about point C so that I can isolate the force in EF. So working over here, I've got the moment of C has to be equal to 0. Okay. So I take the moment about this point. What I have here is I have 300 newtons at a moment arm of 3 meters. Now, relative to point C, this is going clockwise, which is negative, so I have to call that a negative moment. Okay. This force is going through the point, this force is going through the point. So the other one I have, oh, I'm sorry, the distance on this is not 3 meters, my bad. The distance on this is going to be 4 plus 4, 8 meters. Okay, hopefully you guys can see that. So I've got 300 at a distance of 8 meters. And then I have here another force Fe, and this is going to be a negative moment as well because it's also going clockwise relative to point 3 at a distance of 3 meters. Okay. So when I solve this, as you can see, you have, this would be 2,400, you divide by 3. Okay, when I move this over, I actually get that FEC is equal to minus 800. Okay. Because it came out minus, my assumption that it was in tension, okay, I'm sorry, what am I thinking of here? Let me get this fixed here. That's not EC, that's EF. This time I'll fix it correctly. Okay, so my assumption that it was in tension was actually incorrect. So EF, the force in member EF, is going to be 800. The units on that are newtons, and it's going to be in compression, right? Since it came out negative, my assumption about it being in tension is incorrect. So I've got that, I've got EF, I've got EC. The last one I have to deal with is the force in BC. Okay, I've used some forces in the Y. I'm using some of, I've done a moment about point C. I've got lots of options. I could take, for example, if I wanted to, I could take the moment about point E if I wanted to. Since these forces are concurrent, I can isolate this. I'm going to just go with some of the forces in the X direction for this last piece. Again, looking at the overall object. So when I do that, I see I've got a minus 400 going to the left, right? So that's a minus. I've got 4/5 of FEC, which actually we already know. So I'm going to put, instead of writing that down, I'm just going to put in the value directly. Thank goodness for erasers here. So I've got 4/5 of 500, okay, which we knew from here. Okay, this is going to be positive, and then let's see, I'm just making sure I've got this one. I've got 4/5 of EC. Okay, I'm going to have EF, which we just solved, and that's in compression, so that's minus, right? It's going off to the left. Okay, and the last force I'm going to have, which is what I'm actually solving for in this case, is BC. And just let me make sure I got that right. So I've got the minus 400 here. I've got BC going to the right there. I've got EC, 4/5 of EC going to the right because it's in tension. And then I have my EF, which was going this way in compression. Okay. When I solve for that, I've got, this thing, go through here. We're going to have, so this is 400. This right here is going to be a positive 400. So I got minus 400 plus 400. Cancel each other out. And FBC will be just 800 exactly. 800 newtons. And that will be in tension as I originally had estimated. Okay. And that concludes this example of using the method of sections for a truss.